All right, everybody. This will be the last chapter for your final. This will be chapter 10. And this one is a continuation, so to speak, of the last chapter, drawing Lewis structures. Here we're going to talk about sort of putting some numeric values to those structures and looking at what geometries they actually have versus just what they look like on paper. So if you are a big fan of drawing the Lewis structures, I think you'll like this one. If that was a little more difficult for you, this might take a little more studying for you. Okay, so let's just jump straight on into this like we always do. Okay, so first thing we're going to talk about is molecular geometry and then VSEPR theory. VSEPR is valence shell electron pair repulsion theory. And essentially what VSEPR helps us to understand is where in space, so in 3D space, remember, so now we're taking those Lewis structures off the page and putting them into 3D space. And VSEPR theory is going to help us to do that. So if we break down this name, valence shell electron pair repulsion, VSEPR for short. And if we break that name down, okay, so first we have the valence. So remember that's our outer electrons, valence shell, our most outermost electrons. And then pair, so obviously we have pairs of electron, and repulsion. So remember, two like charges are going to repel each other. Okay, so what this is talking about is how like charged particles, in other words electrons is what we're talking about here, how these are going to push away from each other. And we can use this to predict molecular geometries of compounds based on the number of electron groups attached to the central atom. Okay, so for instance, if we have 4 things attached, then generally speaking we know that's going to be a tetrahedral geometry. And we're going to look at some of those. Okay, so the most important factor in determining the geometry is minimizing. So we want to minimize the relative repulsion between electron pairs. So we want to spread those electron pairs out just as much as we can. Because the further they are together, okay, that's causing strain between the pairs. And it's essentially raising our molecule up in energy. So remember I told you we always want to lower the energy of a molecule whenever possible. So if we spread them further apart, that's going to bring our energy level down. Whereas if we squish them together, not only are they repelling each other, but mathematically we're also raising the energy level of that molecule. Okay, and down at the bottom it says the geometry of molecules or ions reflects the arrangement that favors minimal electron repulsion. So that's what we're after here. Minimal electron repulsion. Okay, so where do we start with all of this? So the first thing we need to do is we need to start from a good Lewis structure. Okay, so a good Lewis structure predicts the number of valence electron pairs around the central atom. And then we have each lone pair of electrons constitutes one electron group or one on the central atom. So in other words, so each lone pair is one electron group. Okay? Each bond constitutes one electron group on the central atom. So every lone pair, this is one group, and every bonding pair, that's also one group. Okay? So regardless of whether it's a single, double, or triple bond, it's still just one group. So if instead I had, this is obviously not possible, but if instead I had a triple bond here, this is still just one electron group. It's not 3. While we're talking about bonds, and I may bring this up again later, but I don't want to forget to talk about this because this is something I don't know if I mention in the Lewis structure video, so I want to make sure I tell you now, early on in the video, while you're still listening, right? Okay, so in terms of bond length, so a single bond is our longest bond, a double bond is in the middle, and then a triple bond is the shortest. Okay, so just be aware of that. So as you add more electrons into a bond, so as you start to create a stronger and stronger bond, the atoms are held closer together. Okay, so that doesn't really go with anything we're talking about right now. I just wanted to make sure that I get that out before it gets too late. So I may ask you about that on the exam. Okay. So example here. So we have the ammonia molecule. Well, here we have the central atom is nitrogen, of course. Okay, all hydrogen atoms are attached to the nitrogen, and then we have a lone pair. Okay, so if we wanted to count up how many electron groups, and we'll continue calling these electron domains, but just electron groups is fine. Okay, if we want to count up, we have 1, 2, 3, 4. Okay, so there's 4 electron domains around this atom, or around the central atom. Okay, we'll look at what does that mean exactly. So how does VSEPR theory come into this? Okay, so based on the number of electron groups attached to the central atom of the molecule, that's how we determine the structure with VSEPR. So it's based on how many electron groups are around the central atom. Okay, so the arrangement of the atoms attached to the central atom minimize the relative repulsion. So just what we said before. So in other words, we just want to spread out those groups as much as possible. Okay, so the arrangement of atoms attached to the central atom dictates the compound structure. Okay, the electron pair geometry and its shape, which is the molecular geometry. So notice the distinction here. So we have 2 types of geometry. We have the electron pair geometry, but we also have the molecular geometry. So the electron pair geometry is just what it sounds like. Okay, so where do I have electrons? How many domains do I have? Okay, what's the geometry? The shape, or in other words, the molecular geometry, have to do with the actual atoms that are attached. Okay, so when we talk about electron geometry, we only care about how many electron domains. But when we talk about actual molecular geometry, now we only care about bonding pairs. Okay, so we only care about the pairs that are actually bonded to atoms. So if we take a look at ammonia again, so NH3, if we look at its electron pair geometry, remember it has 1, 2, 3, 4. Okay, so it has 4 electron domains. Okay, so we're going to call this tetrahedral, and we'll learn all these names in just a second. Okay, so that would be the electron geometry. But what if we want to know the molecular geometry? Well, we know there's still a lone pair here. Okay, but right now, we're not going to account for that. We don't take that into consideration. So if I want to know the molecular geometry, it's just 1, 2, 3. Okay, and it turns out this is going to be trigonal bipyramidal. And we'll talk about exactly why that is in just a few minutes. Okay, so that's really all there is to it in terms of determining electron geometry and molecular geometry. The only thing more that you need to know than what I just told you is basically now you have to know what these shapes are called. Okay, so what is it called if I have 4 domains? What is it called if I have 3 domains? Okay, but that's the only other thing you have to know. That's basically all of VSEPR theory. Okay, so what are these shapes I'm talking about? Well, they basically are 5 arrangements, or in other words, families, of electron groups around the central atom. Okay, and there's types of electron groups surrounding the central atom. So they can be atoms, or they can be lone pairs, just like we saw before. And the 5 basic types, and we'll look at each one of these individually. So they can be linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Okay, so those are your 5 basic families. And then within some of these families, we can break them down depending on if they have all electrons, lone pairs, if they have lots of attached atoms, and they start to take on different names based on that. Okay, so here's our basic families. Notice there's a couple more than 5 here, and that's because, like I say, they can kind of start to take on a little bit different characteristic depending on exactly how they're shaped and how many atoms are actually there. Okay, the first one is the easiest. Okay, so here we go, linear. Why linear? Because all 3 atoms fall in a straight line. Okay, so if we have a central atom with, so say AX2, okay, we're going to spread those 2 X groups, whatever they are, out as much as possible around the central atom, which is A. Okay, so you're going to try to maximize this angle. Okay, so it turns out 180 degrees, of course. If we have just 2 things, that's our max angle. Okay, and then we have, so that's for 2 things around the central atom. And notice here we have everything bonded. Okay, so we'll talk about whether, what the shapes are with bonded atoms versus if they're not in just a second. Okay, next one, if we have 3, we have trigonal planar. Okay, so trigonal, because there's 3 things, so like a triangle, so tri. Okay, Y planar. Okay, so trigonal planar. Let's break this name down. Okay, so tri for 3, planar because it's all within the plane of the board, or of the slide, if you want to look at it that way. Okay, there's nothing coming towards us. There's nothing going inward. Okay, it's all just in one flat plane. So if you imagine like an XY plane here, all of the atoms fall within that plane. Okay, next one, bent. Okay, so this is similar to water. That's a good way to remember bent. Why bent? Because if we had linear, it would be like this. Okay, obviously not that long. If we had linear geometry, it would look like this, so without the two x's, obviously. Okay, but that's not what we have. We have a bent geometry because it's not quite linear, but I still only have two things attached. And in the case of water, and in all cases, that's because of a lone pair here. We'll look at that in a little bit. Okay, so that's bent. Next one, tetrahedral. And then again, bent is basically in the plane as well. Tetrahedral. Now this is the first one we have that isn't just a planar molecule. Okay, so this is like your methane, CH4. That's your most basic tetrahedral molecule. And in this, notice we have, so we talked about this in the Lewis structure video, but let's talk about it again. Okay, if I have a solid block like this, so a bolded block, okay, that's going to be, so we call this a wedge. That's going to be coming towards you. So in other words, out of the board. So if it's just a plain line, this is in the plane. Okay, this is in the plane of the board. But if it's a bolded line that's coming towards you, call that a wedge. And if it's dashed line, it's going into the board. So we call this wedges and dashes. That's the kind of drawing this would be called a wedge and dash drawing. Okay, and so it's probably a little bit better represented by the ball and stick model. So notice you kind of have that bent shape going in and out of the board, and then you have a second bent molecule in the plane. Okay, and that's again to maximize the distance between those bonding pairs. Keep in mind, everything we're doing here is trying to maximize the distance. Next one, trigonal pyramidal. Okay, so this is similar to tetrahedral, but we kind of basically just have one group pulled off. Okay, so again, you have this sort of bent shape going in and out of the board, and then you kind of have another leg here. And so you can imagine making sort of a pyramid out of this. Okay, so that's trigonal pyramidal. Okay, trigonal bipyramidal. So now this is very, very similar. So let me try to draw that pyramid again so you can actually see it. Okay, so something like that. Okay, so you have like a three-sided pyramid. Okay, next one is trigonal bipyramidal. Okay, so this is essentially the same thing, but now it has like two pyramids. So trigonal pyramidal is one pyramid. Trigonal bipyramidal, okay, well now I have bi, so now I have two pyramids. Okay, so it sort of looks like this, and this is 5 geometry, so 1, 2, 3, 4, 5. So if you look, there's like a trigonal planar molecule in the middle, and then surrounding it, you have like two pyramids kind of thing. Okay, so that's trigonal bipyramidal. Next one is seesaw. Why? Because it looks like a seesaw. Okay, so we have like a linear group, and then like a bent group coming together. And it sort of gives you a geometry that looks like a seesaw. So if you were to rest this on the board or on the table like this, you could rock it back and forth. So you can imagine this going up and down, and this going up and down. Okay, so we call that one seesaw. Next one, octahedral. Okay, so this is when we have 6 things. This is most common with transition metal complexes. Same thing with bipyramidal too. Well, not always. And this is essentially the same thing as trigonal bipyramidal. But instead of having 3 things around the central atom like we do here, so that we only have 3 things, now this is we have 4 things. Okay, so we have this sort of square planar structure, which the one we'll look at next, and then we also have like 2 pyramids kind of shape up top. Okay, and we just call that one octahedral. The last one, square planar. So this is one with 4 again, but instead of being tetrahedral, instead of being 3D in space like our tetrahedral, this one is just flat in the board. So it's square, because you can draw a square. It's planar because it's within one plane. Okay, so those are all your basic shapes. There's not a whole lot more to know than that, but we're going to break down each one of these individually and look at some of the angles and look at, well, what happens, why is it this shape? Why is it bent and why isn't it linear? There's only three atoms. Why is it not linear? Okay, we'll look at each one of these together, and we'll look at them in greater detail. Okay, so the first one we'll look at is linear geometry. And here we have 2 examples of linear geometry. We have BeCl2 and we have CO2. Okay, so both of these have 2 electron domains, and both of them have 3 atoms. Okay, so we have 2 electron groups attached to the central atom, and we have a bond angle between the electron groups of 180 degrees. Okay, so remember, we're always trying to maximize this distance. Okay, that's our big focus here. Basically, that's all of VSEPR theory. Okay, and here we have 2 examples. So we have one example with 2 single bonds. We have one example with 2 double bonds. Remember, and you can really tell from this picture, our single bonds will be longer than our double bonds. Okay, but they both only count as 1 electron domain, or 1 electron group. Okay, so my number of groups here is still 2. Okay, so it doesn't count as 4 because I have 2 double bonds. But anyway, so the point is, they're going to spread out as much as they can, and they're going to end up in this straight line linear geometry, and the distance between them will be 180. This is one of the easiest ones. Okay, the next one, so trigonal planar. So this is when you have 3 surrounding groups. Okay, so you have 3 electron groups attached to the central atom, with each electron group occupying a corner position of it on a triangle. Okay, so the bond angle here is 120. Okay, so you have this triangle. Okay, then between each bonding group, so this angle is always going to be 120, unless there's some outside factor. And we'll talk about things that divert that, such as having a double bond. Okay, so here we sort of shorten this angle, or we raise this angle. Okay, and we sort of shrink this angle. Okay, so up to 121.9 and 116.2. Okay, so this is a special case. So there are some special cases I'll expect you to know, but not every single one of them. The main thing I want you to remember is that the bond angle here is 120. Okay, that's trigonal planar. Next one, tetrahedral. Okay, so here's a 4 electron group surrounding the central atom, with electron groups occupying a corner position of a tetrahedron. Okay, the bond angle here will be 109.5. So make sure you know this number. That's a real common number, because tetrahedral is one of the biggest geometry, or one of the most common geometries for a 4 or 5 atom molecule. Okay, so make sure you know 180, 120, 109.5. And so this example is methane. So if you just draw the Lewis structure for methane, it looks like a square planar molecule. But in all reality, it's actually a tetrahedral geometry. Okay, and so what that means is you sort of have 2 bent molecules stuck together. Okay, so you have a bent molecule in the plane, and then a bent molecule going in and out of the plane. Okay, and then our bond angle again will be 109.5. Okay, and these all represent tetrahedral geometry, and it's named after this shape, which is a tetrahedron. So if you're into board games that use dice or something like that, you're probably familiar with that shape. Next one, trigonal bipyramidal. Okay, so here we have 5 electron groups. Okay, so electron groups occupy positions in the axial and the equatorial. So our axial is up and down. So you can kind of think of it like the axle of a car. So if it could rotate. And our equatorial positions are always the ones on the side. So this is the same with octahedral when we get there. Hey, again, when you draw the Lewis structure, it looks like a pretty flat molecule, but in all reality, you have what looks sort of like 2 triangles stuck together almost, or 2 pyramids stuck together, hence the name bipyramidal, right? When in actual 3D space. Okay, in our bond, we have 2 different bond angles here. So when you have 2 different shapes like this, you're going to end up with 2 different bond angles. Okay, so around the equatorial, it's 120. So just like our trigonal planar. So this is essentially a trigonal planar molecule with a linear molecule stuck to it. Okay, so we have our trigonal planar molecule. So that's our 120 bond angle. And then we also have this linear molecule, but notice, okay, this is a right angle. So what's always the angle for a right angle? 90 degrees. Okay, so that's what you end up with. So you end up with 2 90-degree angles. Well, several, but you can kind of see what I'm saying. So one here and one here. And then you end up with 3 120-degree angles. Okay, with that trigonal planar molecule. Okay, our next one, octahedral. So this one we have 6 groups. Okay, and again, this is one where we have equatorial and axial in 3D space. Okay, so when you see something like this, where we have 1, 2, 3, 4, 5, 6 groups around the central atom, you'll know that it's octahedral geometry. It's the only one it can have, as far as I know. So in this, we have, very similar to the last one, where we had this trigonal planar molecule around the center. Here we have a square planar molecule. Okay, and then we have 2 axial as well. Okay, so you have basically a linear molecule and a square planar molecule coming together. Now, notice what's interesting here is that all of the bond angles are 90 degrees. So between each of these square planar, it's 90 degrees, and then between each of the axial positions, it's also 90 degrees. Okay, so this one's kind of easy to remember. Okay, and all positions of this molecule are equivalent. Basically, if you were to turn this in any direction, you end up with the same molecule. Okay, that one's not too bad. Okay, so here we say, we'll talk about resonance structures a little bit. So to achieve the best arrangement, the compound's electrons group must have bonds, and all of the bonds must be equivalent. Okay, meaning that even though we draw this molecule with the double bond here, okay, in all reality, it's not necessarily in that position. It could also be here or here. Okay, so that's what it's saying. So energetically speaking, they all have to be equivalent. Okay, and what we end up with is what we call resonance structures. Okay, and what this means is that we can move that double bond around, and it's all the same structure. Okay, and in reality, all 3 of these exist simultaneously. So the molecule isn't necessarily with the double bond in that place, isn't necessarily with it to the side, but it actually is a mixture of all 3 of those. Okay, and we call this resonance structures. And you'll see these signified with this double-headed arrow. Okay, that's letting you know that these are all equivalent. Okay, and if we take a look at the electron geometry versus the molecular geometry here. Okay. So if we just count up the number of electron domains, we have 1, 2, 3. Okay, so that would be our electron geometry is trigonal planar. And our molecular geometry, now we want to count only the bonding domains. So we don't count lone pairs for this. And we still see 1, 2, 3. So they're both the same. And sometimes that's the case, and sometimes it's not. Sort of just, you have to assess it based on the molecule. So for instance, this is not a real molecule, but say we had, for some reason, 3 minus. Okay. Our electron geometry would be 1, 2, 3, 4. Okay, so we would have either a square planar or tetrahedral. But our molecular geometry would just be 1, 2, 3, so it would still be trigonal planar. Okay, so that's what we're talking about when we talk about the difference between electron geometry and molecular geometry. And remember, resonance structures would be all 3 of these. So it just means that it doesn't necessarily exist like this, it doesn't necessarily exist here, or it doesn't necessarily exist there. But in fact, it's all 3 of those, okay, simultaneously. Okay, so we've pretty much talked about this already, but we've talked about the fact that molecules are 3-dimensional objects. Okay, so we have to describe their shape in terms of related geometry figures. We said linear, bent, T-shape. Okay, so all the ones we went over. Okay, and the geometric shapes have the following characteristics. Corners that indicate positions surrounding the atom, angles. Okay, so basically what we've already talked about. This is a good example in H3 of one where we have a difference between our electron geometry and our molecular geometry because of this lone pair. Okay, it also affects our bond angle. Okay, so if we just want to look at our electron geometry first, we would have 1, 2, 3, 4. So we have tetrahedral. I'm sorry, for our electron geometry, tetrahedral. And then for our molecular geometry, we just have 3. Okay, so we would probably call this trigonal pyramidal, something like that. But notice our normal tetrahedral bond is 109.5. Okay, but when we put a lone pair into this position, what it does is it pushes back down on these 3 bonds because it occupies more space. So since there's nothing sharing these electrons, they're going to be closer in on the atom and they're going to be bigger. Okay, since there's nothing taking any of their size on. Okay, nothing taking any of their charge on. Okay, so they will push these other bonds down. So notice that it lowers this angle to 107 and it will raise this angle. Okay, so this angle is lowered and this angle is raised. And that's just from that pushing effect. So remember, we always want to maximize the space between our electrons. Okay, so valence repulsion, remember? Valence shell electron repulsion. Okay, so that's part of what we're talking about when we talk about VSEPR. Okay. Okay, so structure influences molecular properties. So the chemical and physical properties of molecular substance depend on their structure. Of course they do. Okay, so a lot of reactivity is based around what electrons are accessible to other atoms or other molecules. Okay, so this can be the skeletal arrangement. In other words, just how are they bonded? Okay, it could be the type of bonding. So is it ionic bonds, polar bonds, covalent bonds? Do they have multiple bonds, for instance? So we know that it's harder to break a multiple bond than it is a single bond. Do they have lone pairs? Do they have a lone pair that can take a hydrogen from another molecule, for instance? Okay, and then what's their 3-dimensional shape? Okay, so just how accessible is that lone pair, say, to bonding, or how accessible is that single bond to being broken? Okay, so the structure really, really plays a lot of effect into their reactivity. And we talked about this already, but we can have some distortions. So we said that lone pairs like to push, or they push away, and they sort of modify the angles of a normal atom. So they require more space, and they need more space, and it causes distortion. Okay, so we have the types of atoms bonding. Okay, that affects the size of the atom, can also cause distortion. The types of bond can cause distortion. So do I have a single bond, or do I have a double bond, or a triple bond? Okay, if I have a double or triple, that's going to take up more space, and it's going to be closer to the central atom than, say, a single bond. And then just what is the molecular geometry? Okay, so it's going to cause them to vary a little bit based on how big are the bonds, how many lone pairs do you have, what types of atoms do you have? Do I have a big atom? Do I have a small atom? Do I have several double bonds? Do I have several lone pairs? Okay, that's going to affect my ultimate molecular geometry. So for instance, we have methane, NH3, and H2O. Okay, so with methane, we just have 4 bonded hydrogens. So 4 bonding domains, 4 electron domains. So we have this angle of 109.5. So this is our undistorted tetrahedral. Okay, but now, when we go to ammonia, now we know we have 1 lone pair. Okay, remember that lone pair is going to push down on these other atoms, the other electron domains, and shrink that angle a little bit. Okay, and then lastly, in the case of water, and water is a really good way to remember this. Okay, in the case of water, okay, you have 2 lone pairs. Okay, so you have a double dose of distortion. Okay, so notice how much smaller this angle is. Okay, so 104.5. Okay, and here we say not all bonds are identical. Why? Well, because if we have a double bond versus a single bond, okay, that's going to be a whole nother pair of electrons. They're also going to be closer together, and they're going to be more centralized. So it's going to cause more distortion than, say, just a normal single bond, which would not cause distortion necessarily. Okay, so the number of electrons between are different. Okay, and then the electronegativity of the atoms. Okay, so how far does it lie towards, say, for instance, between boron and fluorine? You know, our electrons may lie a little bit further towards fluorine than they do towards boron. Okay, and that's going to cause a different shape than compared to, now I have an electronegative atom with a double bond versus some single bonds of hydrogen. Okay, that's all going to affect our angles. And I'm not going to expect you to know every single one of these. What I might expect you to know, though, is what effect it has. In other words, would it be strong, bigger or smaller? How is it going to affect that bond? Okay. So because not all bonds are identical, the angles of the atoms will be slightly different. Okay, next up we have ammonia again. And I'm not going to spend too much time going over this since we already talked about it. Just remember that that lone pair has the effect of pushing this down. Okay, so if you kind of take your hand and put your palm towards the ground and sort of curl your fingers in, that's kind of the effect that I'm looking for. And if I was in front of you, that's what I would do to visualize this for you. Okay, here's a chart that summarizes all the different types of geometry and all of their angles. Make sure you know this. I can ask you just simply, what's the bond angle in trigonal planar, what's the bond angle in linear, anything like that is fair game. And then know if I have tetrahedral bent or anything like that, what those angles are. Especially for things like water ammonia that we've talked about a lot. And the list continues. Again, just make sure you have a good feel for these. And if you understand how they're shaped, that shouldn't be too big a deal here. The toughest ones are things like where they're just kind of almost random numbers, seemingly, like 109.5. Okay, so notice it just says less than 109.5. That's all you really need to know. And then 120. So if you can understand the shapes, you should be able to figure out those angles. Okay, so here we have some examples of placement of lone pairs around the central atom. Okay, so if we look at the geometry of the molecule, again, it's always going to want to minimize the electron repulsion. So what pair will be broken first kind of has an effect, or the fact of electron repulsion has an effect on which bond you would break first. Okay, we probably won't really get into that too much. Okay, but we want to occupy a position with a structure that has the space to allow for it to spread out. Okay, so in other words, that lone pair is going to go in the place that offers it the most room. Okay, so geometries which do not have minimizing position around the central atom, where the bond angles are equally spaced out, like linear, trigonal planar, and tetrahedral and octahedral. Okay, so these are examples where, since all the positions are equal, there's really no best place for them. There's the most common place, okay, but not really. Okay, so geometries which do not have minimizing positions. Okay, so linear, trigonal planar, tetrahedral, octahedral, and that's because all of the bonds are equivalent. Okay, but there are some of the geometries where we do have that, and we looked at some of those already. Okay, so I'm going to skip through some of these slides because we've already talked about most of it. But here's some things we haven't talked about. Okay, so placement of electron lone pairs, where do they go? So I said there's certain places where we will put these lone pairs versus others. Okay, so for instance, with trigonal bipyramidal, the lone pair will always occupy the equatorial position. Okay, so they're always going to go to the side here. Okay, they won't go in the axial position. And if you think about this, it should make sense. So even if you weren't sure about this, if you just use your VSEPR theory to think about it, okay, you don't even have to know that this information. You could sort of determine it, okay? And hopefully you're learning that that's sort of the better way of learning science, is to understand the reasons why, and then from there you can predict what the answer should be. Okay, so the reason it would go on the side in the equatorial position is because, remember, this angle is 120 degrees. Okay, where the axial angle is 180 or 90 degrees, excuse me. So if I was to put it in this axial position, now I have 90 degrees, 90 degrees, 90 degrees. Okay, so that's not exactly as far away as it could be. Whereas here I have 120, 120, and then I just have two 90 degrees rather than three. Okay, so it's more spaced out. Okay, and that's how you end up with things like seesaw type geometry. Okay, or even if you have two, it's the same idea. So this we call T-shaped, so this is another special kind. So if you remove you put two lone pairs, in other words, if you remove two bonding pairs and change them with lone pairs. Okay, so if we take our trigonal bipyramidal and remove two, Now we end up with T-shaped, okay, called T-shaped because it looks like a T. Okay, but notice our two non-bonding pairs go in our equatorial position, again, because that's the biggest angle. Okay, so if we remove 1, we end up with seesaw. If we remove 2, we end up with T-shape. And if we remove 3, okay, we end up with linear. And it looks just exactly like a linear molecule. These are molecular geometries, by the way. Okay, our electron geometry stays exactly the same. It doesn't change a bit. Okay, but these are examples where your molecular geometry and your electron geometry are different. Okay. And then if we have, and I know I'm kind of skipping over some of the text, but I'm trying to give you all the text just by talking normally, not trying to read it to you. So if you want to read it, go back in a couple slides and you can go over that. Okay, now, what if we're talking about octahedral? Well, remember all the positions in an octahedral are essentially equivalent. Okay, but what we'll do is we'll always put the non-bonding pair in the axial position. So unlike our trigonal bipyramidal, where it goes in the equatorial position, when we're dealing with octahedral, it will always go in the axial position. So one lone pair occupies either the equatorial or axial position of the central atom, and 5 other groups are attached to the central atom. So this is a little bit higher level and sort of to inorganic chemistry, but you'll always put it in the equatorial position and not into the axial positions. I'm sorry, I said that backwards. I had to think for a second. I said that backwards. Always go in the axial position, not into the equatorial position. Okay, so if you remove 1, you end up with this, square pyramidal. Okay, so it's square, and then you have pyramid shape. Okay, so square pyramidal. That's if you remove 1 lone pair. Okay, if you remove 2, now we end up with square planar. So notice, we didn't remove this one and then this one. What we removed was the 2 axial positions. And then we're left with a square planar molecule. And the reason we do this is if you were to look at the energy levels for removing these 2 axial positions, it's more favorable than removing the equatorial position. So you want to remove the 2 furthest away from each other, in other words. Okay, but if you do that, you result in a square planar molecule. Okay, and we'll talk about this relatively briefly, but if we have multi-central atoms, so for instance we have atoms with a carbon chain, or you just have, multiple interior atoms, okay, each of the atoms will have its own geometry. So you would look at these individuals. So for instance, let's look at this carbon. Okay, so if we look at its electron domains, 1, 2, 3, 4, so it's tetrahedral geometry. And if we look at its molecular geometry, we see that's in a tetrahedral shape. Okay, but that doesn't mean that this nitrogen over to the left is also tetrahedral. It doesn't mean that whatsoever. It has its own shape. So if we look, it has 1, 2, 3, and then we know it probably has a lone pair there. Okay, so this is going to be trigonal pyramidal. Okay, so tetrahedral electron geometry, trigonal pyramidal, molecular geometry, and then if we look at this rightmost carbon, 1, 2, 3, so it's trigonal planar. Okay, then the oxygen is all we have left. Okay, so this would have bent just like water. Okay, so you just look at them individually, determine their molecular structures or geometries just individually. So you kind of just treat, almost just like cut the rest of this off. So if you're looking at the nitrogen, you would just cut this bond and cut these bonds and just forget all about it. Okay, then determine your geometry from there. And then move on to the next atom and do the same thing. Okay. So that's basically going over the same idea. Okay, so we talked about drawing things with 3D, especially in the Lewis. We already talked about this. So a straight line is in the plane, hatched or a dash is in the plane, and a wedge is coming out of the plane. So I won't belabor that point too long. But that way you understand how to read these shapes. Okay, so these are some sort of step-by-step rules on how to predict electron pair and molecular geometry. Hopefully I've shown you this enough time, but let's just go over the rules formally. That way you have these to look back on if you get stuck on anything. Okay, so identify the central atom and draw the Lewis structure. Okay, so you have to start with a good Lewis structure on these. That's the only way to do this. Okay, then determine the number of atom groups or lone pairs. Okay, so basically what it's saying in the second step is determine your electron domains and how many bonding or how many lone pairs. Count the number of atoms bonded to the central atom, not the number of bonds. Okay, so then next look at bonding atoms. Okay, so first look at bonding groups, then look at bonding atoms. Okay, so look at whether you have double bonds or single bonds. Remember that those are equivalent when you're talking about sort of electron domains. Okay, we know that they have different repulsion values, but in terms of electron domains, they're the same. Okay, so just determine your atom groups and your lone pairs. Okay, then determine the geometry. So remember, your electron geometry takes into account all of the electron domains, and your molecular geometry just takes into account the actual bonding pairs. And so the main thing here is to use your VSEPR theory. So if you're thinking like, well, how do I know it's bent and not square planar or something like that? Well, you have to remember back to your VSEPR theory, remember about your repulsion, and think about, okay, so what's going to push what? Well, I know the lone pair is going to push this away, or I know this double bond is going to push this away a bit more. Okay, and that's how you have to think about this. Okay, so let's try this one. So it says determine the electron and molecular geometry for the compound ammonia. Okay, so we've looked at this one a couple times, but try it again. So try drawing your Lewis structure for ammonia, and then we'll talk about it. Okay, so what's the first thing you want to do here? First thing you want to do, draw your electron dot structure, in other words, your Lewis structure. Okay, so hopefully you were able to come up with this Lewis structure for NH3. Okay, so go back and make sure you can draw Lewis structures pretty easily. Okay, count the attachments and lone pairs. Okay, so I have 3 bonding pairs. I have 1 lone pair. Okay, so we're looking for electron and molecular geometry. Okay, so I have 3 attached hydrogens, and I have a lone pair. Okay, so electron geometry, I have 4 electron domains. Okay, so that's going to be tetrahedral. Okay, then I have 3 bonding pairs, so that would give me trigonal planar. I'm sorry, trigonal pyramidal. Why pyramidal? Because remember that this group is going to push those down. So it won't end up being just a regular trigonal planar, but actually will have that pyramid shape. Okay, so there's a few examples here for you to try, along with the answers. So I'm going to let you go over these on your own. They're all in the slides for you. So if you do have any trouble with these, please just let me know. Okay, but I'm not going to take the time now to go over them, and that's strictly because I'm trying to keep this a little bit shorter for you guys. But if you do get stuck on any of these, please feel free to contact me. Okay, this next little bit here, determining polarity. So I went over this in the Lewis structure video, so hopefully you went over that. Okay, but remember, when you're talking about polarity, you're going to look for an electronegative atom attached to a not so electronegative atom. Okay, then you can draw on your lone pair. So let's look at CO2 up here. So we know that comparing oxygen to carbon, okay, oxygen, if you remember back to our periodic trends video or lesson, oxygen is further towards fluorine, so it's the more electronegative compared to carbon. So you'll draw in your dipoles like this. And if you have dipoles that are exactly opposite in this way, that's not going to be a polar molecule because they cancel each other out. But if you have dipoles that aren't canceling each other out, so for instance we have one going this way, one going this way, so we have an overall dipole in the middle here, that's going to be a polar molecule. Okay, so I believe I go over that in a little more detail in the Lewis structure video, so go back and review that if you're still struggling there. Okay, this is a good example of what I mean by canceling out or not canceling out. Okay, so this kind of gives you an idea in 3D space. So if they're exactly opposite, that would be nonpolar. If you have just one going in a different direction, that would be polar. basically, if they all pull in opposite directions, you have a nonpolar molecule. But if you have an overall pull in a single direction, a stronger pull in a single direction, you end up with a polar molecule. So hopefully this visual representation helps you to see that. Okay, so let's try this one. So which one of these is polar? Okay, so draw your Lewis structures and try to write in your dipoles real quick, and then we'll go over it together. Okay, so first we need to draw out their Lewis structures and then try to draw in our dipoles. So by now, you probably know that water is a polar molecule. Okay, so this probably wasn't too tough to just make that decision on, but hopefully you'll be able to draw on these dipoles. So remember, the arrow will always point towards the more electronegative atom. The cross will always be on the side with the less electronegative atom. And if we want to indicate these partial charges, we'll use a lowercase delta. So this little squiggly s kind of thing as a lowercase delta. Okay. And then if we notice here, we have an overall dipole in this direction. So that's, of course, a polar molecule. Okay, then CO2, we draw its Lewis structure and write in our dipoles. We can see that they're pointed exactly away from each other. Okay, so this would be a nonpolar molecule. So it has no net dipole. That's what this is called, by the way. This is the net dipole. I haven't really said that. Okay. Okay, in this last section, we'll talk about two theories behind chemical bonding, and we won't get too deep in this. I mainly just want to introduce them to you and let you get a feel for them, but not dig too deep in them. Okay, so a couple problems with Lewis theory in terms of chemical bonding. Okay, so firstly, it only predicts the general property trends. However, it doesn't give good numerical predictions on bond strength or bond length. Okay, so it's good sort of to make predictions with, but if we're talking about concrete numbers, we're not going to get that from Lewis theory. It gives a good first approximation of bond angles and molecules, but it can't be used to determine the actual bond angle, so we need more information than that. Okay, and it cannot explain the concept of resonance, so why do we need to draw resonance structures according to Lewis theory? It's not really, you can't get it from that. Okay, and it doesn't predict the correct magnetic behavior. So in other words, Lewis theory is good, it really is, but there's more to it than that, is what it's trying to say. So we have two theories here. So valence bond theory and molecular orbital theory. So valence bond is abbreviated VB. Molecular orbital theory is abbreviated MO. If you get into inorganic chemistry, you're going to look a lot at molecular orbital theory. So valence bond theory is the electron density of the valence electrons is localized between the bonding atoms. Okay, the valence electrons located in half-filled atomic orbitals overlap to form molecular bonds. Okay, so in other words, this is talking about the overlapping of valence electrons to form bonds. So kind of the opposite of what we're talking about in VSEPR, where there we're talking about the repulsion of electrons. Here we're talking about half-filled orbitals overlapping to form the bonds, so single, double, all that kind of stuff. Okay, then if we talk about molecular orbital, so the electron density of the valence electrons is delocalized within the molecule, and the valence electrons occupy molecular orbitals that spread throughout the molecule. So what are we saying here? So valence bond is telling us that no, the electrons exist inside of their orbitals, and those overlap, and where they overlap, they form a bond. But they're still localized in where they sort of, you approximate them to be. So they're still localized within their orbitals. Molecular orbital theory says no. The electrons are delocalized throughout the entire atom, okay, and then they just happen to fill whatever molecular orbitals are there. And the truth is that it's somewhere in between these two. So neither one of these is completely correct, neither one of them is completely false. But the truth lies sort of in between all of these theories, and they all come together to be a powerful tool. Okay, so here we have sigma and pi bonds. So a sigma bond is the electron density found between two atoms. Okay, the electron density is found within the plane of the bond, and it can be formed by hybridized or unhybridized orbitals, and we'll get into hybridization in just a second. Okay, and every molecular bond contains a sigma component, and that's basically the single bond. So sigma, you can think single bond. Okay, so anytime I have a double or triple bond, I start from a sigma bond, a single bond. Pi bond, okay, so in other words, sigma bond is in the plane. Now a pi bond is what starts to come up and out, so inward and outward and up and down in the plane. So this pi bonds are responsible for your single, or your double and your triple bond. So a double bond has only one pi component, a triple bond has two pi components. Okay, so let's look at this. So sigma bonds look something like this. Okay, so sigma bonding occurs when electrons in their atomic orbitals overlap with each other, and the overlap happens within the plane of the bonds, or of the board, you could say. Okay, so sigma bonds are when two atomic s to s orbitals overlap, or when two p to p orbitals overlap, but only if they're head-to-head. So this first statement, so s to s, so if I have two s orbitals, remember this sort of ball shape, if they overlap, okay, then that can form a sigma bond. Or if I have my p orbitals, so this is why it was so important to know the three sets of p orbitals, so if these overlap, that also forms a sigma bond. Okay, so either s to s overlap or head-on p orbital. Okay, so notice this is a sigma bond. So the head-to-head is a sigma bond. Well, what's the opposite of head-to-head? If you're saying that's a sigma bond, well, it's a pi bond. So if instead they're parallel, okay, and they start to overlap in this direction, so sort of in this curved shape, that's when we start to get pi bonds. Okay, so if they're head-to-head, it's sigma. If they're parallel, it's a pi bond. And there is a certain distance when we start to talk about overlap. That's the logical distance or the actual distance of a bond. So if we squish the electrons all the way together, we'll have really high energy. So energy is here on our y-axis, and then bond length is on our x-axis. So if we just squish the two orbitals as close as we can, they're really going to repel each other. So we're going to have high bond energy. And as we start to spread out a little bit more, we start to go down in energy, okay, until we get to this valley. And at some point, if we start to pull them apart far enough, then we start to go up in energy again. So essentially, there's this sort of happy medium distance, okay, where we actually form the bond. Okay, so that's why we have certain bond distances, and they're not just kind of all over the place. There's a happy medium there. Okay, so pi bonding occurs when the electrons in the atomic orbitals overlap sideways. In other words, sort of in that parallel. Okay, and these form above and below your sigma bonds. Okay, so that's this type of overlap, like I was saying. Okay, that kind of, they'll start to curve in, like you see here. Okay, so this is our example. So your sigma bond would be here in the middle, and then your pi bond would be surrounding it here and here, and then you also have two more in and out of the page. We'll look at that all together in just a second, another slide. Okay, but just remember, it's sideways versus head-on with your p orbitals. Okay, so valence bond theory involves the overlap of atomic orbitals. It incorporates VSEPR theory and the idea of hybridization. Okay, so we know that the valence electrons inside of the orbitals have to be spin paired. A molecular bond results when electrons in their atomic orbitals overlap. In other words, they're interacting by overlapping. Okay, and there's a total of 2 electrons in each bonding orbital. We know that. Okay, and the valence electrons in an atom reside in either the quantum atomic orbitals or the hybrid atomic orbitals. In other words, there can be some electrons that are unhybridized on the same atom where they also have hybridized atomic orbitals. So that gets a little confusing. And I know most of this is probably not going to sound that obvious at first, but I think once I show you some of the images, it will start to make more sense. Okay, so when there's direct overlap of atomic orbitals, it can explain the experimental data. Valence bond theory says that the atomic orbitals of the central atom had to undergo hybridization. Okay, so in other words, if valence bond theory can't explain just based on atomic orbitals, in other words, explain the shape of the overlap, then we have to hybridize. And hybridization of the central atom's atomic orbitals happens so that the bonding atoms, valence electrons, can bond, in other words, overlap with the central atom's valence electrons. And we'll look at, I know I keep saying hybridization, I haven't really defined it, we'll get there. Okay, the molecular shape is determined by the geometry of the interacting orbitals. Okay, and the electron pair geometry of the molecule, the ion dictates the type of hybridization around the central atom. So in other words, the shape of the molecules dictate how it's hybridized. Okay, a problem with valence bond theory is it can't explain the molecular bonding for molecules or ion that bring an odd number of valence electrons. So not every atom has an even number of electrons, so what happens then? Okay, so this is what we mean when we start talking about hybridization. So it's the transformation of the central atom's atomic orbitals, and they undergo this transformation to accommodate the valence electrons from the bonding atoms. Okay, and the type of hybridization that occurs on the central atom's atomic orbitals corresponds to the electron pair geometry. So in other words, exactly what shape are they? Okay. And remember that the electron geometry is determined by the number of bonding atoms and the non-bonding electrons. Okay, so what we're talking about here is this type of hybridization. So when we talk about hybridization, we're talking about S, P, and D hybridization. So in linear, we have SP hybridization. Trigonal planar, we have SP2, tetrahedral SP3, and I'll show you how we're counting this. Okay, so what exactly are we talking about here? So what we're talking about is that these unpaired electrons, okay, form bonds with these unpaired electrons, and they start to mix the orbitals together. Okay, so how does a 1s orbital interact with a 3p? Well, the explanation there is that they start to form hybridized orbitals. Okay, so in this particular case, we're able to overlap s orbitals with these p orbitals without hybridizing. So this is an example of a non-hybridized molecule because we're easily able to overlap our two s orbitals in the right direction with our p orbitals here. Okay, so no need to hybridize. Okay, so what's an example where they do hybridize? So for instance here, CH4. Okay, so what we have here is we have 4 s orbitals, and then we have the orbitals around carbon. Okay, and what has to happen for these to overlap correctly is it has to go through hybridization. Okay, and this is just strictly in terms of shape. Okay, so a lot of this bonding theory is based around the shape of the orbitals. So what has to happen is the 2s and the 2p have to come together, and they form an sp3 orbital. Well, they form 4 sp3 orbitals. Okay, so why is it sp3? Well, so you get the s from here, p, p2, p3. Okay, so that's how you count it, and I'll show you exactly what I mean in a second. And that forms these sp3 hybridized orbitals. So notice we put 4 in, we also get 4 out. Okay, so these come together, and they sort of take on this morphed shape to give you that tetrahedral geometry. So without doing this, you can't really form those bonds in order to make up CH4. Okay, so you have to sort of morph their shape in order to get that good overlap. Okay. So how do you count this? So the first one is always S, the second one will always be P, and if you just label your electron domains this way, you'll end up with the right answer. So this would be SP, here we have S, P1, P2, S, P, P2, P3. Okay, then once you run out of P, you go into D. Okay, that's it though. Okay, so that's how you assign your S and P, and I'm pretty much going to leave it there. Okay, because I think digging too far into this is not a good idea right now. Okay, so I did want to jump to this slide because it shows a lot of these ideas coming together. Okay, so it shows how the pi bonds are formed, it shows how the sigma bonds are formed, and then it shows how the hybrid orbitals interact with everything. So around this central carbon, we have sp, p2, p3. Would that be D? Yeah. Well, no, excuse me, because these are unhybridized orbitals. Sorry. So the hybridized orbitals would just be s, p1, p2. Okay, but it has to take on that hybridization in order to form a good overlap with the s orbital of the hydrogen, and in order to form this good head-to-head overlap with the oxygen here. Okay, so that's why you have to go through this hybridization, is to get that good overlap. And I know this is probably not so obvious just yet, but when you study it more in Chem 2, hopefully it will come together a little bit better. But then notice we have our pi bonds forming above and below our sigma bond. Okay, and I just wanted to jump to this slide. So notice if now we have a triple bond, okay, you have one up above and below, and you also have one going into the board and one coming out of the board. So you just keep adding that pi overlap when you start adding in the extra bonds. Okay, so jumping to molecular orbital theory, and this is pretty much where we'll end up. Okay, so molecular orbital theory differs from that of valence bond theory in that it makes the assumption that when an element forms a bond, you actually create new molecular orbitals. So it doesn't have anything to do, according to molecular orbital theory, it doesn't have anything to do with hybridizing. That doesn't come into play here. Okay, no, what happens is the orbitals come together and form a completely new set of orbitals. Okay, so electrons entering these molecular orbitals follow the Pauli exclusion principle, and they follow Hund's rule. Okay, so in this theory, valence shells or valence electrons are delocalized. Okay, and the bonding electrons are not located specifically above or below the plane of the bond. Valence electrons are in orbitals called molecular orbitals spread out over the entire molecule. Okay, so basically this theory says, no, when orbitals come together, they form brand new orbitals, and the electrons just file into those orbitals based on the Pauli exclusion principle and based on Hund's rule. Okay, and they're just scattered throughout, they're spread across the entire molecule. It's not just localized between two atoms. Okay, so this is kind of what it looks like when you draw these molecular orbital diagrams. So if we have the simplest molecule here, so two hydrogen coming together, so each hydrogen brings a 1s. Okay, so these come together, and when two orbitals come together, they form two orbitals. So always you form the same number of orbitals, the same number of new orbitals, as what you bring to the table. And when two s orbitals overlap, they form a bonding orbital, and they form an anti-bonding orbital. Okay, and we call this the sigma. So sigma 1s would be how you call this orbital. Okay, and then its anti-bonding would be the sigma star 1s. Okay, so you always form bonding and anti-bonding. And if we have more electrons in the bonding orbital than compared to the anti-bonding, or as long as it's greater than, you have a bond. So this would still be a bond if we had a third electron, still be a bond. But if we were to add a fourth electron, you basically have no bond here, because your anti-bonding and your bonding essentially weigh each other out, so they cancel each other out, so you don't end up with a bond. Okay, and these orbitals get really, really big. I'm going to try to find one of the large. Here we go. So if you remember back when I talked to you about oxygen a little bit ago, you started to see some of these. Here's a closer shot of one. Okay, so you start to build and build these molecular orbitals, and they get really, really big. But you can use them to predict certain properties about the atom. So here's a good example. Okay, so you have 2s, 2s, then 2p coming together. So notice you form bonding, anti-bonding, bonding, bonding, anti-bonding, anti-bonding. Okay, I'm not going to expect you to be able to draw these, but I just wanted to introduce it. Okay, honestly, these are really fun when you get to learn to draw these, but there's a lot that goes into drawing them that we're just not going to get into in this class. Okay, so that will be your last chapter for the exam, and for the final, I hope you enjoyed the class so far. I know you've got a busy week coming up, so good luck with your exams. And if you're coming along with me to Chem 2, I will see you there.